Hello everyone, thanks for tuning in. Today I'm going to talk about my research titled Flood Analysis of Bridge Stream Interactions Using Two-Dimensional Models. This research is funded by TIDC with matching funds from VTrans, and we greatly appreciate their contribution. And of course, thank you to everyone who has helped support this research. The format of this presentation will cover motivation and goals of the research, methodology, 2D HEC-RAS development, screening framework development and application, the intervention modeling, and the overall conclusions of the work. So first, the motivation and overall goals of the research. The increase of flood events across the world have shown the vulnerabilities in transportation infrastructure. Other parts of the world have studied how human-impacted climate change is showing increasing trends in the frequency and magnitude of precipitation, and in some places this has led to extreme flood events. And the damages of these events can cost communities millions of dollars in repairs. So our research has shown that bridge rehabilitation programs and designs usually consider the specific location of a single bridge with little to no consideration for up or downstream locations. There also seems to be minimal studies that quantify or observe bridge stream interactions on a river scale, and these studies struggle to prioritize and assess the impacts these interactions can have, making it difficult to communicate to stakeholders. So the objectives of the work aim to solve these challenges. We want to understand bridge-river interactions on a river scale for rivers of different gradients and how these interactions impact the river up and downstream. And we develop a framework to evaluate these interactions to identify infrastructure that would be most sensitive to flood mitigation interventions. So next, I'll discuss the methodology. The three study reaches used for this research are the Black Creek, Mad River, and Otter Creek. The Otter Creek study reach has 9 road bridges and 5 rail bridges. The Black Creek observes 3 road bridges, and the Mad River observes 16 bridges. And NHD data shows that all the rivers have a range of slopes from very low to high. So when we plot this, you can see the difference between the Mad River, the Black Creek, and the Otter Creek. The Mad River has the greatest range of gradients and is the steepest river. The Otter Creek is the longest study area, but has very long stretches of very low and low slopes, and the Black Creek is the smallest study area and features similar slopes to the Otter Creek. In order to better observe these rivers under transient conditions, 2D HEC-RAS models were made for each study reach. The HEC-RAS models made for the Otter Creek and the Black Creek were done by previous graduate students, so I will go over how the Mad River model was developed, since that's the one that I focused on for this presentation. To build the 2D HEC-RAS model, open source LiDAR data of the river was collected. This is combined with bathymetry data collected by Du Bois and King, who did a previous 1D model of the river to develop a 2D model. So these two main features combined with the two-dimensional mesh allow a user to simulate flood events. To simulate the tropical storm Irene event, additional features had to be added to the model. So to observe these 16 bridges you see on the left, additional tributary data had to be included, which you can see on the right. Using a drainage area ratio method and estimating peak flow using stream stats, hydrographs were developed and shaped for each tributary. Since only one stream gauge is found downstream in the Mad River, the similar method was done to calculate the upstream boundary condition for the model. When all this information is put into the model, the downstream output hydrograph is compared to this USGS observed hydrograph. So this is what USGS observed during Tropical Storm Irene. And when you compare the HEC-RAS output, you can see how closely the two hydrographs match. The modeled hydrograph, so the HEC-RAS output, is evaluated using a Nash-Sutcliffe efficiency test, and the values from this test can range from -infinity to 1. The closer to 1, the closer the modeled results match the observed results, and values are considered calibrated if they're above a 0.7. The Tropical Storm Irene event achieved a value of 0.94, telling us that the results are very similar to the actual flood event. To observe multiple flood events, StreamStats was used to estimate peak flow annual exceedance probabilities of 1%, 2%, 4%, and 50%. The Tropical Storm Irene event was scaled to observe all of these flood events on the Mad River. So now that the model is able to be observed under multiple flood events, a screening framework was developed using the HEC-RAS results to identify bridges that would benefit from intervention to reduce flood damages. So this is the screening framework, and it combines channel gradient and specific stream power to identify bridges and locations that would see a significant impact if an intervention was implemented. And in this study, an intervention is defined as an action that would reduce negative flood impacts such as scour or overtopping. So the first thing we look at is whether or not there's bedrock present in the area. Doing interventions in an area with bedrock is not cost effective or realistic for a community. And in these cases, an intervention is not likely needed in this area, but interventions could be done up or downstream to reduce any negative flood impacts seen if there are any in this particular location. And then we begin to look at different combinations of gradient classifications and specific stream power values that would determine maximum impact from an intervention, variable impacts, or minimal impacts. So this is the Mad River bridge locations with the screening framework applied. You can see the bridge name, the gradient classification, the specific stream power value at each simulated flood event, and whether or not there's a presence of bedrock. If we follow the framework, you can see every red row is there, mostly because of the presence of bedrock, but you can still see that there's high specific stream power values as well as changes in gradient. So to reiterate, interventions done up or downstream do have the potential to reduce specific stream power at these locations without the need of excavating bedrock. If you look at the Main Street Bridge as an example, its gradient classification is high. The upstream reach has a moderate to high gradient, so it's different than the Main Street Bridge area. And all of the specific stream power values are greater than 35 and 300, so they're greater than that stabilization and critical threshold of specific stream power. So all flood events, it shows that it could have a significant impact if an intervention was performed. Where if you look at the Waitsfield Covered Bridge area, it has the same gradient classification as the one upstream, but it still has high specific stream power values, so it has a variable impact. We don't know whether it will be as significant as others. So this framework is also applied to the Otter Creek, as well as it's applied to the Black Creek. Using the framework, I selected multiple locations in each study reach to observe how changes to the bridges and the river can impact other locations up and downstream. So for this presentation, I'll only go over one example that was done in the Mad River. The Waitsfield Bridge is classified as a location that has potential to see impact from interventions. So from stakeholder input, the intervention area is actually just upstream of the bridge, and it includes Couples Park on the left and privately owned land on the right side of the stream, and the arrow indicates the bridge. On the right is a cross-section looking downstream from the project location. Here you can see the water surface elevations of the various modeled flood events at the project location. So going through the different storm events with Tropical Storm Irene showing the highest water surface elevation. The proposed intervention is actually to remove the berms and reconnect the floodplain at the Q2 event, which you can see in this black line. When this is done, we originally look at the water surface elevation during Tropical Storm Irene, and then during the intervention, you can see a large reduction in water surface elevation as well as an increased water inundation. So how does this impact the bridge itself and the structures throughout the river? Well, the top panel shows the water surface elevations for each bridge under baseline conditions. And then once the intervention is in place, you can see a large reduction in water surface elevation throughout the river, and no bridges are seeing overtop conditions like you would see during the baseline condition. Then we look at specific stream power. So specific stream power in baseline conditions show unstable conditions even during Q2 events, and then it increases to critical conditions above that 300 watts per meter squared threshold. However, under intervention conditions, you can see some stabilization at the bridge at Q25 events or lower, and then the values remain unstable but not critical until you see events equivalent to Tropical Storm Irene. On a river scale, we can see many reductions of specific stream power, and in some cases stabilized values, providing much safer bridge conditions. And so these observations were done for multiple types of interventions, including floodplain lowering, bridge span increase, berm removal, and culvert modification for all study reaches. And from these observations, we came to the following conclusions. So the screening framework proved more useful in moderate to high gradient rivers where changes in gradient are more dramatic and frequent. The calibrated model showed how site-specific interventions have cascading, non-intuitive consequences throughout the study reach, demonstrating the value of 2D transient modeling. Longitudinal cascading impacts are more extensive in low gradient rivers, but is highly dependent on bridge river physical characteristics. And given site-specific interventions, the benefit of reducing stream power is more pronounced in varying in moderate to higher gradient rivers. So how is this useful? Well, the screening framework developed in this research can be employed for resource prioritization, holistic design of bridges, and bridge and river rehabilitation projects. The research demonstrates the value of performing 2D transient hydraulic modeling for reach scale bridge river analysis and design. And the screening framework can be applied to other rivers under similar geographic and climatic conditions, so other places within the New England region. The study also serves as a proof of concept for a methodology to quantify these interactions on a river scale, and is able to start to address some stakeholder concerns about cascading impacts of planned bridge projects. There are always some limitations. We assume the results to this are variable. Additional research may result in supplemental parameters such as land use or even additional specific stream power thresholds that have not been explored in this current version of the framework. And some recommendations that we have would be to apply the framework to other rivers in the Northeast region. Some more 2D HEC-RAS modeling of rivers, as well as additional intervention modeling in the Mad River and other rivers in the Northeast region. Thank you very much for listening.